Hello, welcome again to the lecture series on control systems engineering. In this session, let us discuss a very important topic, this Bode plots. We'll learn how to construct Bode plots for the given transfer function. Also learn how to find gain margin, phase margin, and system stability. Identify the system type number. Estimate peak magnitude, peak frequency, bandwidth, and steady state error. And explain M circles, N circles, and Nichols chart. Okay, first let us understand what Bode plot means. You all must have seen an equalizer in your music system. The equalizer on the y-axis side, you have seen magnitude in decibels. On the x-axis, you have seen the frequencies. So when I lift this up, amplification happens. If I push down, attenuation happens. At a given instant, you might move these points at different positions and you join them. Probably you move this one here, move this one here, maybe move this one here, again here, 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 and so on like this. You join all of them, right? Maybe like this. Join all these points. Then we get a frequency response curve. This is what we call it as Bode magnitude plot. Bode magnitude plot. So, accordingly, wherever you are lifting this up, that frequency gets amplified. If you're pushing down, that frequency gets attenuated. So based on that, in which frequency range you are interested in, right, get better response, you can do so. So this is a good example of a Bode plot. Let us understand how to draw such Bode plots and how exactly the poles and zeros of the open loop influence this. Right? Suppose you are pushing it up, this button, probably the zero is playing an important role. If you are pushing it down, the pole is playing an important role. Right? So Bode plots are, we also call them as logarithmic plots, or we call them as corner plots. In Bode plots, there are two types. One is magnitude in decibel versus frequency plot, and phase angle versus frequency plot. So here, normally we draw this plot on a logarithmic sheet. Logarithmic sheet, or we call it as semi-log sheet. Semi-log sheet. That's why it's called logarithmic plot. The advantage is you can have very high range of frequencies. Suppose I start here with 0.1, I can go up to 10,000. If I start with 1 here, probably I can go with 100,000. Very high frequency range you can represent on x-axis. Okay. Now you see here 1 divided by 0.1 is 10, log 10 is 1 cycle we call it. So 10 by 1 like that, 1 cycle, 2 cycle, 3, 4, 5. This is a 5 cycle semi-log sheet. We don't start with 0 here. The reason is log 0 has no definition. So that way, depending on our convenience, we choose a starting frequency. Here we mark magnitude in decibels. Suppose you take any value, parameter, to convert that value into decibels, just multiply by log to the base 10, take log of this value to the base 10 and multiply with 20. Then this will become in decibels. Okay, this is magnitude in decibels. This is frequency. On this plane we draw this plot. Here the phase angle in degrees versus frequency we draw. So thus it is known as phase angle plot. It is known as magnitude plot. Okay. Now suppose, I think it is wrong. This is 0.1. 0.1. 1 by 0.1 is 10. So it is decade. 1 cycle. If the opposite side is 20 dB, adjacent side is 1 decade. If I join these 2 points and draw a line, that line will have a slope of 20 dB per decade, and it is positive. Okay. Suppose take 20 dB on the opposite side, 1 decade on the adjacent side, and join this, and going downwards it is minus 20 dB per decade. It is negative slope. Right? So know that. So we express this slope in terms of decibels per decade. This is the form the Bode plot transfer function, the open loop transfer function will be given. Always note that open loop transfer function will be given to you. This is a constant gain factor K. These are finite zeros. This is a quadratic zero. These are number of poles at origin. These are finite poles. This is a quadratic pole. Whatever be the problem given, you always reduce that problem into this form. That is 1 plus something into S. 1 plus something into S, like this. This form you should reduce it. Otherwise you may go wrong. So this is what I said. Now let us learn how to draw Bode plot for these factors. Okay. Anyway, I will come back to this. First, if you want to draw Bode plot for a constant gain factor K. So magnitude in decibels is 20 log mod K. By chance in this example K value is 32. Magnitude in decibel is 20 log 32. This will become 30 decibel. Phase angle of a positive constant is 0 and phase angle of a negative constant is minus 180 degree. Now how to draw the Bode plot for a constant gain factor? Let us go to this log sheet. This is say 0.1, 1, 10, 100, 1000, 10,000. This is frequency in radians per second. Okay, right, sir. Here we'll mark 0 decibel, plus 20, 40, 60. Same as minus 20, minus 40, minus 60, like this. So 20 log K, the magnitude is 30 decibels. 30 decibels, mark here. And simply draw a horizontal line. It has no slope. So that is the Bode plot of, say, K value is equal to 32. Phase angle, you can simply draw 0 degree line here if it is a positive constant, and minus 180 degree line if it is a negative constant. Okay, right. Next, how to draw Bode plot for 1 by S. This is pole at origin. Magnitude in decibel is 20 log 1 by S. S to the power of minus 1. So it is minus 20 log S. S equal to j omega. Modulus of j omega is omega. So you will get m equals minus 20 log omega. So it is in the form y equal to mx. So you can say as omega varies, magnitude varies with a slope of minus 20 dB per decade. Okay. What is the starting magnitude? If I put omega is equal to 0.1, log 0.1 is minus 1, minus minus plus 20. So you'll get 20 dB. What is phase angle of 1 by S? Already you have studied in polar plot. Phase angle of 1 by S is minus 90 degree. Now you want to draw the Bode plot of this. So suppose this is 0.1 and this is, say, 1. When omega is 0.1, let us say magnitude is 20 dB. When omega is 0.1, magnitude is 20 dB. As omega varies, magnitude varies with a slope of minus 20 dB per decade. Minus 20, so come down. 1 decade means this point and this point. Join these 2 points and draw a line. This is minus 20 dB per decade. Okay. This is plot of 1 by S. When you want to draw the phase angle plot of this, let us say it is 0 degree. This is minus 90 degree. Simply draw a minus 90 degree line. So it's phase angle of 1 by S. So now go to this plot. When omega is 0.1, magnitude is 20 dB. It varies with a slope of minus 20 dB per decade. Join these 2 points and draw a line. This is what 1 by S plot is. And phase angle of that 1 by S is this one. Okay. Now let us do it for 1 by S square. So you'll get minus 2, 20, minus 40. It is minus 40 log omega. Slope is minus 40 dB per decade. So omega is 0.1, log 0.1 is minus 1 minus half minus plus 40 dB. And angle is minus 180 degree. Now the plot is 0.1, say 1. Now the magnitude is, when omega is 0.1, 40 dB. Take 40 dB. Minus 40 dB per decade. Join these 2 points and produce. This on this you write minus 40 dB per decade. And this is a plot of 1 by S square. And angle of this will be, this is 0, minus 90, minus 180. This is minus 180 plot. Angle of 1 by s square. So same thing I have plotted here. When omega is 0.1, magnitude is 40 dB. Minus 40 dB per decade. Join these 2 points and plot. Plot of 1 by s square. Correct. And minus 180 degree line. Okay. I'll draw on this 1 by k. Again minus 180 degree line. Suppose there are 3 poles. It is s cube. Then slope will become minus 60 dB per decade. Phase angle will become minus 270 degree. Okay, that's what I have done here. Okay, suppose it is s only, numerator. Mostly 0 at origin. Only thing is the slope will be plus 20 dB per decade. If omega is 0.1, this will become minus 20 dB. Phase angle will be plus 90 degree. So omega is 0.1, magnitude is minus 20 dB. 20 dB per decade. Join these 2 points and produce. The angle is plus 90 degree. Okay. Same way if it is s square, you will get this plot. If it is s cube, you will get this plot. And s square phase angle plot is 180. For s cube phase angle plot is 270. That's how we can draw the Bode plot of constant gain factor, poles at origin and zeros at origin. Now, suppose you have a finite pole 1 by 1 plus STA. Now you see here, magnitude is 20 log modulus of 1 by 1 plus STA. So what happens to this will go up means minus 1. That minus will come here, 20 log 1 plus STA. Substitute s is equal to j omega. Then minus 20 log under root 1 square omega square ts square. You will get this. Let us make some approximation. If omega Ta value is very much less than 1, compared to this is small, omega square ts square. That's why magnitude is minus 20 log 1, which is 0. Omega Ta greater than 1, then this is negligible. Then it is magnitude is minus 20 log omega Ta. Okay. So these two will meet when omega Ta is equal to 1. Omega Ta is equal to 1. Or omega is equal to 1 by T. This frequency we call it as break frequency, or we call it as corner frequency. That's why it's known as corner plot also. What's the meaning of that in the Bode plot? Let us say it is 0. This is a minus 20 dB line. Okay, this is 0.1. This is 1. This is 10. This is 100. Okay. Suppose I have a factor like this, 1 by 1 plus 0.1 s. So break frequency is 1 by 0.1, that is 10. Up to the break frequency, the magnitude depends on 1, so magnitude will be 0. After that, it varies with a slope of minus 20 dB per decade. So how do we draw the plot now? Let us say this is 10 now. I'll mark this 10. Up to 10 it is 0. Then it is minus 20 dB per decade. This is how it varies. So you can say minus 20 dB per decade. This is break frequency. Correct. Exactly at break frequency, magnitude cannot be 0. This is also equal to 1 means 20 log root 2. I'll get minus 3 dB actually. So the plot will be something like this. These corrections we have to apply. But in straight line approximation, simply we draw like this. Okay, this is minus 3 dB. That is the error that we commit if you apply straight line approximation plot. Now let us talk about phase angle. Phase angle is tan in minus, because it is pole, tan inverse of omega Ta by 1, omega Ta. So I keep on giving values for omega. Phase angle can be 0 when omega is 0, and phase angle will be minus 90 degree when omega is equal to infinity. So we can do the calculation. Another way of doing is, let us say phase angle is equal to 0 up to 1/5 of the break frequency. And we'll take phase angle minus 90 degree after 5 times the break frequency. You want more accuracy, probably you can make 1/10 and 10. Okay, in between it varies as a straight line. So in this case, phase angle is 0 up to 2, 1/5 of 10. Phase angle is minus 90 after 50, 5 into 10. In between you can join by a straight line. So now let us draw phase angle plot. Maybe up to 2 is this point. After 50 means here. Okay, assuming this is minus 90 degree line. Up to 2 phase angle is 0. After 50 phase angle is minus 90 degree. In between it varies as a straight line. Okay, so we are introducing errors here. Actually, this is how it should be. Only thing is, we ensure at break frequency the angle is exactly minus 45 degree by doing like this, because tan inverse 1 is 45 degree. Okay, this I have shown here. Up to break frequency, the magnitude is 0. Then it varies with a slope of minus 20 dB per decade. Phase angle, 1/5 of break frequency, the phase angle is 0. Then it varies from 0 to minus 90. Then it remains minus 90. Okay. Similarly, we can do Bode plot for a finite zero. So again the same if I do, I'll get the break frequency as 1 by T1 and slope as plus 20 dB per decade. And phase angle is 0 up to 1/5 of break frequency. Phase angle is plus 90 after 5 times the break frequency. Then take this as an example. One break frequency is 50 radians per second. 1/5 and 5 times. So what you can do is, in this case, up to 50 the magnitude is 0. Then take decade, this 5 to next. You take 20 dB here. Draw this line. So on the phase angle side, up to 10 the phase angle is 0. After 250 the phase angle is, up to 10 the phase angle is 0. Phase angle is plus 90. Okay, plus 90. Okay, this is how we can draw that. So it is plus 90 degree and 0 degree. This is 1/5 of break frequency, and this is 5 times the break frequency, and this is the break frequency, and this is plus 20 dB per decade. Okay, right. Now this is what I have shown here. Finite zero now. Okay, up to the break frequency the magnitude is 0, then plus 20 dB per decade. Join these 2 points. Phase angle, same thing, 1/5, 5 times. Okay, just join this and I have drawn. Okay, here whatever example I have taken, 1.05 now. So I have taken 1 plus 0.05. 0.05 means break frequency is 20, right? So 1/5 of 20, 4, up to 4 here. I think that is also a mistake. 0. Then 5 times 20 means 100. Then it is 90, plus 90. Sometimes I draw this to differentiate from the line already existing. Okay. In between you join by a straight line. Okay. Done. Same way if there is a quadratic pole. What should happen? There are 2 poles. Slope will be minus 40 dB per decade. Break frequency is square root of reciprocal of coefficient of a square. That is the break frequency. Then phase angle should be taken as 0 up to 1/5 break frequency, and phase angle should be taken as 2 poles of minus 180 degree after 5 times the break frequency. And this is for quadratic 0. This is the break frequency. Please remember, square root of reciprocal of coefficient of a square. This we can prove separately. So slope is plus 40 dB per decade, and phase angle is 0 up to 1/5 break frequency. Phase angle is plus 180 after 5 times the break frequency. So these are the fundamentals you must know, then we can easily draw the Bode plot. Now to make you understand, let me do a simple example. Let me work out a simple example. Suppose g of s is given as 3.16 divided by S into 1 plus 0.1 S. There is a constant gain factor K. There is a pole at origin. There is a finite pole. K equal to 3.16. Magnitude is 20 log 3.16. That is 10 decibel. And the phase angle is 0 degree. If I take 1 by S, slope is minus 20 dB per decade. Magnitude is given by minus 20 log omega. If I start my graph sheet with 0.1, log 0.1 is minus 1, magnitude is 20 dB, and phase angle is minus 90 degree. 1 by 1 plus 0.1 is the finite pole. Break frequency is 1 by 0.1, 10 radian per second. Slope is minus 20 dB per decade. Phase angle to be taken as 0 up to 1/5 of 10, that is 2. Phase angle should be taken as minus 90 after 5 times the break frequency, that is 50. Okay. If the minimum break frequency is greater than 0.5, you start with omega is 0.1. Just a clue. Less than 0.5, better whatever minimum frequency is there, 10, but you better start with in terms of 1, that is 0.01, 0.001, like that. So now how to draw the Bode plot? Very simple. Now take this, assume this is your sheet, correct? This is your 0 decibel line, 20, say 40, this is 20, this is 40, this is 60, say minus 20, minus 40, minus 60, like this. Then this you draw, this you draw, this you draw, like this. This sheet is available anyway. 0.1, 1, 10, 100, 1000, 10,000. Okay. Let us draw Bode plot. Magnitude of 3.16, 10 decibel. Draw 10 decibel horizontal line. This is K equal to 3.16. Then 1 by S plot. Then omega is 0.1, magnitude is 20 dB. Slope is minus 20 dB per decade. This is 1 by S plot. 1 by 0.1, break frequency is 10. Up to 10, magnitude is 0. The slope is minus 20 dB per decade. Minus 20 come down. 1 decade you choose. This is, you write here on this, minus 20 dB per decade. Here also you write minus 20 dB per decade. And it is a plot of 1 by 1 plus 0.1s. Okay, after drawing all these lines, let us draw the resultant plot. Okay, at this point, 1 minute. At this point, this is contributing 10 dB, this is contributing 20 dB. 20 plus 10 is 30 dB or 30 dB. This line has a slope of 0 dB per decade. This has a slope of minus 20 dB per decade. So the resultant should have minus 20 dB per decade. Okay, join these 2 points and produce this line till the next break frequency. There is a break frequency here. Up till it is minus 20 dB per decade. At this point, this line is added to this. This lope is minus 20. This minus 20 will become minus 40 dB per decade. 20, 40 dB per decade. Join these 2 points and produce. On this you write minus 40 dB per decade. Okay, and this becomes your resultant plot. Of course, you want to apply the correction factor of minus 3 dB, we can apply, and we can draw the actual plot. But this is sufficient. This is sufficient. Right. This is linear line approximation plot. Straight line approximation plot. So now you want to draw the phase angle plot. For that, okay, assume this is your semi-log sheet. This is 0 degree line. Let us say this is minus 90 degree line, minus 180 degree line, plus 90 degree line, plus 180 degree line, and 1. Okay. So it is 0.1, 1, 10, 100, 1000, 10,000. Okay. This is 0 degree, minus 90, minus 180. Okay. Plus 90, plus 180, plus 270. You mark this. Then let us draw phase angle plots. 1 by S is, this is 0 degree. Another one is minus 90 degree. Draw minus 90 degree line. That is 1 by S plot. Other one is 1/5 of break frequency up to 10, the phase angle is 0. After 50, phase angle is 1/5 of 10, 2, sorry, I'm sorry. This is 1, this is 10. So 2 means here. Okay. Up to 20. After 50 here, 10, 100. You can see there will be a 5 here. After 50 it is minus 90 degree. Let us join these 2 points. Just to differentiate this line from this line, I have drawn like this. Okay, let us mark wherever there are corners. Mark as A, B, C, and S. Last corner, stop. Now let us find the resultant plot. Let us draw that. To begin with, here this line is contributing 0 degree. If you want to call it as line 1, line 2. Line 1, line 2. Line 1 is contributing minus 90 degree, line 2 is contributing 0 degree, so total is minus 90. Come to corner B, again it is minus 90. Come to corner C. Line 1 is contributing minus 90. Line 2 is also contributing minus 90. Totally minus 180. Come to corner S. It is same. So your resultant plot is varying from minus 90 to minus 180. This is your resultant plot. Okay, that's how Bode plot can be drawn. First, create the table. As per the table, draw the magnitude plot, draw the phase angle plot. Right, later we'll see what can be done with these plots. Only thing is I have taken here a square now. Correct? So you will get minus 40 dB per ticket. I will teach one more example later. Okay, this is 32, 1 plus 0.5 s, s into 1 plus 0.1 is 0.2 s. So 20 log 32, m 20 log 32, 30 decibel, phase angle is 0. 1 plus 0.5 s, this is a finite 0, break frequency is 1 by 0.5, 2 radians, slope is plus 20 dB. 1/5 of 2, that is 0.4, and 5 times 2, that is 10. 0 to plus 90, it varies. 1 by s, slope is minus 20 dB per ticket, magnitude is minus 20 log omega. When omega is 0.1, magnitude is 20 dB. Phase angle is minus 90 degree. 1 by 1 plus 0.1 s. Break frequency is this, slope is this. Phase angle is 0 up to 1/5 of 10. Phase angle is minus 90 after 5 times 10. 1 by 1 plus 0.2. 1 by 0.2 is 5 radians per second. Slope is minus 20 dB per decade. Phase angle is 0 up to 1/5 of 5, that is 1. Phase angle is minus 90 after 5 times 5, 25. Now we can draw this for this. Okay. You can see that is first 32, 20 log 32 is this one. Okay. Then you have 1 by s plot, this one. Then you have 1 plus 0.5 s, that is up to 20. Then 20 dB per decade, 2 to 2. Join this. Next is 1 by 1 plus 0.1 s, that is up to 10. Then minus 20 dB per decade. Next 1 by 0.2, sorry, up to 10 bar. Up to 10 means this one. Okay. Another one is 1 by 0.5. Another one is 1 by 1 plus 0.2 s, that is 5. This is 5. Then minus 20 dB per ticket. Please, just because I made a mistake, be careful about this. Now let us draw the resultant plot. When omega is 0.1, this magnitude is 20. This magnitude is 30. 30 plus 20, magnitude is 50. Slope of this horizontal line is 0. Slope of this line is minus 20. So minus 20 dB per decade. Take these 2 points and draw the line till it touches the break frequency. Here, first break frequency here. There is another break frequency here, another here. Now from here this line is starting. O stop is plus 20 dB. This plus 20, this minus 20 will become 0 till the next break frequency. From here this line is starting. O stop is minus 20. Add this minus 20 to 0. Minus 20 here dB per decade. Keep your scale on this. Draw till the next break. That is minus 20. From here another line is starting whose slope is minus 20, minus 20, minus 20, minus 40. Minus 40 dB per decade. Join those 2 points and no more lines are there, just produce. That is what will result in magnitude plot. Of course, at each point we can apply the correction factor and get the actual plot. Then same way, draw the phase angle plot. Phase angle of k is 0 anyway. 1 by 0.5 is, that is 0.5, that is 2. That is up to 0.4, phase angle is 0. After 10, phase angle is 90. Point 4, this one, in between you draw. Okay, that's fine. Next is what you have, 1 by s, that is minus 90 degree. Draw that minus 90 degree line. Next what we have, 250. Mark 250. 250. Okay, draw this line. Differentiate, draw one more line here like this. Next you have 1 and 25. 1 and 25. Okay, read very carefully here. This is 0.1, this 1 means this is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, like that you must read. Okay. You got this value A, then B, then C, then D, E, there is here F, and there is here G. And last one, as I said, yes. Correct. Now at A, this is 10 divisions, mark there. No other line is contributing. B again, you see the lines above as well as below. Below this, you have only one line, that is at minus 10, mark that. Come to C. This line is contributing minus 10 division, that is equivalent to 90 degree. This is contributing plus 3 division, so totally it is minus 7, mark minus 7. Come to D. This is contributing minus 10. This is contributing minus 2, minus 12. This is 5, so totally it is 7. Come to E. Minus 10 of this, minus 7 of this, minus 5, 22. Out of this 10 plus 10, so minus 12. So measure 12 from here. Always measure from the 0 line and do it. Come to F. Right now, this point. Minus 10 of this. Minus 10 of this. Minus 20. Minus 8 of this. 28. Plus 10 of this. So 18. Measure 18 and mark. Come here. Minus 10. Minus 10. Minus 10. Minus 30. Plus 10. So minus 20. Here also minus 20. Then you join all these points by straight lines. Okay, and this is your phase angle plot. So here you should write phase angle in degrees versus frequency. There you have to write magnitude decibel versus frequency. So M in dB versus frequency radians per second. You write this. And you write 0.11, 10, 100, 1000, 10,000. Here you write phase angle in degrees versus frequency in 0.1, 1, 10, 100, 1000, 10,000. Okay, draw these plots. Okay, so I have shown the calculation for a number of examples. You can draw Bode plot and practice. Okay, this you have to factorize and do it. This one. Yes. Okay, sir. So now you draw Bode. Let us say gain margin, phase margin. I already explained you in Nyquist plot. So gain margin is already we are done 1 by modulus of G of S HFS at phase crossover frequency. Phase margin is 180 degree plus phase angle of G of S HFS at gain crossover frequency. This I have explained already. So what you do is take the magnitude plot and is your resultant magnitude Bode plot. This is your phase angle plot. This is minus 180 degree line. This is 0 dB line. You have drawn the phase angle plot. Fine. Right. This is what you call it as gain crossover, JCO, and that frequency you wrote, that is gain crossover frequency. This phase crossover, that frequency you read phase crossover frequency. From the gain crossover, you drop a vertical to the phase angle plot. You will get phase margin. Okay, and that 180 degree minus phase angle. Correct. You will get the phase margin. From phase crossover, you drop a vertical to this, you will get gain margin. Reciprocal of that. That's why down. Okay. So here if you get positive gain margin, this is positive phase margin. Then you know that it is not crossing -1 plus J0 point when we draw the Nyquist plot. System is stable. By chance you get gain margin here and the phase margin here, then the system becomes unstable. So this I have already told you how to find gain margin and phase margin using Nyquist plots. There is one more plot, what we call it as magnitude in decibel versus phase angle plot. That also we can draw and find gain margin and phase margin. How to draw this log magnitude versus phase angle plot? G of S, H of S will be given to you. Correct? Write magnitude equation as I was substituting S equal to J omega as well as phase angle equation. Then for different values of omega, take the magnitude, convert the magnitude in decibels by multiplying with 20 log of that value. Then also you take phase angle in degrees. So a number of values of omega you choose, calculate the magnitude, convert the magnitude in decibels by taking 20 log of that quantity. Also you calculate the phase angle the way you used to calculate in polar plot. Then take an ordinary graph sheet. So mark the magnitude 0, 20, 40, 60, 80, minus 20 like this. So there is a minus 180 degree line and there is 0 dB line. On this you mark the points, phase angle and magnitude in decibels and draw this graph. This is what you call it as magnitude in decibel versus phase angle plot. This plot is crossing 0 dB line. This is gain crossover. Then find the phase margin. Here it is called cutting minus 180 degree. This is phase crossover, and measure this value, you will get the gain margin. This is called log magnitude versus phase angle plot versus phi plot. Okay, done, sir. So that's how we can find system stability. And also you understood the relative stability business, right? Larger the gain margin, more phase margin, and more stable the system is. Okay, draw Bode plot for the loop transfer function like this. Or they will give a problem like this. G of s this way, h of s this way, g of s, h of s you multiply, you'll get this. But bring it down to Bode form. You take out 5 from here, you take out 50 from here, then you will get Bode form. Correct? Then assume k is equal to 1, draw Bode plot. And we can find what should be the value of k for a gain margin of 32 dB, what should be the value of k for a phase margin of 60 degree. Like these kind of examples we can find out. We can solve. Okay, so there are many such examples. Look at this. Okay. 1 minute. Suppose an example like this is given. 5 into 1 plus 0.1 s. Yes, 1 plus 0.5 s, 1 plus, okay, 0.6 omega by 50. This is a quadratic equation. Okay, this kind of problems are given. Then how do we draw Bode plot? Using MATLAB. Very simple. Numerator is what? 0.5, 1 plus 0.1. So 0.5 star multiplication. S coefficient is 0.1, 1. That's how it is numerator. Denominator, S means 1, 0. Next is 1, 0. Then 0.51, 0.51. Next, these coefficients. Okay. Right, sir. So these are given. 1205. So 0.6 by 51. Correct? S square, S coefficient like this. So that is F3. Then I am multiplying F2 and F3. Again I am multiplying with F1 so that I'll get the denominator. Okay, sir. This is what you get. Right? This is your denominator. Then say sys transfer function num comma din. Okay. Then you say Bode sys. Then it will draw Bode magnitude plot, Bode phase angle plot. Within no time it will draw and give you. So here another example. Numerator is 10. Denominator is s. 0.2 s plus 1. 0.02 s plus 1. So denominator I have multiplied all of them. Then I say system transfer function num comma din, Bode sys. I will get Bode magnitude plot, Bode phase angle plot. Right. Next you want to find gain margin and phase margin. Add, say margin sys. Then get gain crossover, then it will find phase margin, phase crossover, gain margin. It is given gain margin is 14.8 decibel at 15.8 radians per second. Here. And this is gain margin. Phase margin 31.7 degree and 6.22 radians per second. Gain crossover. it will find the gain margin as well as phase margin. Pretty simple, right? Now there are certain things here. Performance specifications in frequency domain. How does the frequency response of a system related to the expected transient response of the system? In other words, given set of time domain specification, how do we specify frequency response? Okay. To answer this question. Okay. Let us consider a second order system. Omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Let us find three terms: resonant peak, resonant frequency, and bandwidth. To find resonant peak, you know the transfer function you have. Substitute s equal to j omega, you will get this. Differentiate this and get omega value. That omega value is substitute here. You will get the peak magnitude. Correct? You have to differentiate with respect to omega equated to 0. You will get omega. That omega you call it as omega r, because it's the point at which magnitude is maximum. That's why you call it as a resonant frequency. Substitute that omega value here. Correct, and you will get the resonant peak. This is what I have plotted: MR versus omega. Correct, the frequency at which the magnitude is maximum, we call it as peak magnitude or resonant magnitude. Now let us look at our peak overshoot in transient response is what? E to the power of minus zeta pi under root 1 minus zeta square. If the zeta value increases, this value increases. Correct? It will die down. What? E to the power of zeta value increases, this e to the power of this large value. So it will die down. That means peak overshoot will be very small. Here zeta is large means again resonant peak is also small. So resonant peak and peak magnitude, they depend on zeta value. If the zeta value is low, resonant peak is high. If the zeta value is high, the resonant peak or peak overshoot will be less. Correct. And once that is done, probably you know, yes, the settling time, this issues come. Okay, settling is 1 by zeta omega n again. If the zeta is less, time constant will be more. It will take more time to settle. Zeta is high, time constant is small, it will take less time to settle. Okay. Damping relation related to maximum magnitude which occurs frequency. At resonant frequency, a maximum value of the frequency response in PW is attained. Anyway, that's how these two are related. So when I draw the Bode plot at breakpoints, I can find out what is the case and all that thing. From that, it is possible for me to understand the time response behavior. Bandwidth is another important thing. Is the frequency at which the frequency response has declined by 3 dB. from its low frequency or DC value. Look here, this is the 0 dB line. From here you measure minus 3 dB. Okay, that frequency I call it as bandwidth. Okay, magnitude of G of j omega p must be 1 by root 2 G of j omega. Right, that is the definition at low frequency, right? So that's how we are getting minus 3.01 dB. 20 log root 2 I said break 1 plus 1, that is the thing. So now again you calculate the magnitude, substitute omega b, correct, get the magnitude this way, and from this we can find omega. That omega is what you can assign it as omega b when this becomes 1 by root 2. So then you will get omega frequency b. This is the bandwidth. Again, bandwidth depends on zeta. Right? Zetas are small. That means what? Bandwidth will be quite. So this zeta small and again zeta square. Okay. Then bandwidth will be quite high. So I told you about this anyway. As WB increases, so does the natural frequency omega n, implying a decrease in rise time in step response. Correct? As WB increases, so does the implying decrease in rise time, faster to rise, right? This is what I think I explained to you. Okay, right, sir. A greater bandwidth W with a constant damping renders a smaller time constant. Smaller time constant, faster response. Okay. So a larger bandwidth means faster the output of the control system tracks an input. So the usefulness of frequency response specification and the relation to the actual transit performance depends upon the approximation of the system by a second order pair of complex poles. The second order poles of these transfer functions are called dominant poles. If the frequency response is dominated by a pair of complex poles, the relationship between the frequency response and the time response as discussed here are valid. Fortunately, large portions of control systems satisfy this dominant second order approximation. What it means. Suppose you want to understand the behavior of higher order systems. You see here in this system, suppose you have poles here and in this region. But these are the poles which control the system behavior. So this is what we call them as dominant poles. So roots are away, response may decay faster, but these will not allow it to faster. These are the one which will be influencing. That's why dominant poles. If the frequency response of a higher order system is dominated by pair of complex poles, the relation between frequency response and time response for second order system can be applied as an approximation. Okay, that's what we mean by the poles, the roots which influence the system behavior. They are dominant poles. So that's why even if you have a higher order system, we do not have to get into The detailed analysis of higher order system, it is better approximate it as a second order system and understand the behavior. Then there are steady state error specification. You know, steady state error is equal to limit s tending to 0 is r of s 1 plus g of s h of s. Correct? Then you have kp, positional error constant, limit s tending to 0 g of s. kv, limit s tending to 0 s g of s. And ka, acceleration error constant, limit s tending to 0 s squared g of s. You have studied this. Okay, right. I will come to this type identification. Not 2 minutes, you hold on, right? I'll come back to this. So identification of static error constant, that is kp, kv, ka. Suppose you have the Bode plot, get the starting value. Okay. So kp is limit s tending to 0 is at g of s. That's why kp is this. So we can straight away, you can write kp is equal to, from Bode plot you can read 13.85 dB. You can write like this, 20 log k is equal to 13.85. And you can find k also. Okay, that is kp. Okay, because it is g of s, that's the reason. It is, sorry, g of s. Limit s tending to 0, 0 of s g of s. That's why minus 120 dB slope, that value you take. Wherever minus 20 dB is there, then just produce that line. Wherever it cuts, that frequency you take. From that frequency we can find kV. Okay, so that is, you can find kV from here. Okay, value is the asymptote line at omega equal to 1 radians per second. So 20 log kV, so this becomes 1, so it is 20 log kV. So whatever value is there, you just take it, measure it and find kV value. Okay, so minus 20 dB, wherever it cuts 0 dB, see here, right, at omega equal to 1, you are getting 20 dB here. Okay, 20 log kV is equal to 20 dB. Draw the Bode plot, that minus 20 dB line you draw, 10 to the power of 0 is 1. At omega is equal to 1, you get it. That is 20 dB value. Read the 20 dB value and get kV. Okay, so you can also find steady state error. Okay, now let me tell you one more thing. I was talking about type number. Suppose you have a Bode plot. Bode plot. So let us say it is magnitude is given is minus 20 dB. There is a break frequency. Then it is minus 40 dB. There is a break frequency. Minus 60 dB. Again minus 20 dB. This is minus 60 dB. What is the transfer function of this? To begin with, you have to have one slope of minus 20 dB per decade, means there should be a pole at origin, 1 by s. Again, the slope has increased to minus 40 dB, means there should be a finite pole. There is a break frequency, so 1 plus 1 by 5 is 0.2. So this is 1 by 0.2 s. Again, the slope has increased. Again, there is a pole. So it should be 1 plus 1 by 10, that's 0.1 s. Now next, it has decreased. So it should be a 0. So 1 plus 1 by 20, that is 0.05 s. Right. Then again, the slope has increased. There must be a pole. So that's how we can find, if the Bode plot is available, we can find the transfer function. So you can indicate the type number also. Okay, if you want to find k, no problem at all. What is this k value? Suppose this k value is, let us say, 50. Okay. Out of that, 1 by s value is 20. So total value is 50. At 1 by s, omega 1 is 0.1, that is 20 dB. So k value will become 30 dB. So 20 log k is equal to 30. Log k is equal to, so k is 32. We can put that 32 here. That's how we can find even k value. Right. This has been taught. These things are repeated. This also I told you about log magnitude versus phase angle plot. The last one, closed loop frequency response analysis. EM circles are constant magnitude circles. What they are. Let us take g of s is equal to x plus jy, a complex number. So closed loop transfer function is g of s divided by 1 plus g of s. Substitute that complex number. Get magnitude. We'll get like this. So square it up. You will get this way. Let me cross multiply. This is 1x squared plus 2x plus y squared. M squared is equal to s squared plus y squared. Let me rearrange these things. Okay. Then I'll get, if I reorganize, I'll get an equation like this. Okay, let me add m4 to both sides. Okay, I will get an equation like this, this way. This represents an equation of a circle. The center of the circle will be minus m squared divided by m square minus 1. And here this y coordinate is 0. And this is, that is x minus x plus a whole squared plus y plus b whole squared is equal to r squared kind of a thing, right? You got this. Radius will become square root of this, m by m square minus 1. That means I can represent all the closed loop magnitude by a set of circles centering at this point with this radius. What I do, I go on giving values for m. So I'll get the center point, also I'll get radius, and I'll draw a set of circles. Okay, take this x. Also you take this as y. Let us say, let me go on giving positive values for m. I'll get set of circles. I go on drawing the circles. Okay. M less than 1, but greater than 0, right? Here m greater than 1. Okay, I'll get another set of circles. So m is equal to 1 here. It's a line. Now suppose these circles are available. What is the use? G of SHFS is given. Once G of SHFS is given, you can always draw the polar plot. You superimpose the polar plot on these M circles. So every point you are marking frequency, correct? Frequencies you are marking. At a particular frequency, let us say it is cutting this circle. So at that frequency, what is the closed loop magnitude? You can find out. So once the open loop transfer function is given, polar plot can be drawn. Superimposing the polar plot in M circles, closed loop magnitude can be determined at a given value of frequency. That is the use of M circles. Similarly, you want to find closed loop phase angle. Then I use concept called N circles or constant phase angle circles. Again, do the same way. G of S, C of S by R of S. Then angle is okay, x plus jy. Get this. Okay, let us alpha is equal to this. Take tan on both sides. N equal to tan alpha. Then tan of A minus B formula you apply. Reorganize all these things. So doing all the manipulations, finally you will get an equation of this form. Okay, now I can draw a set of circles, keeping this as center, square root of this as radius. And I call these circles as N circles. Okay, so 80, 70, 60, like this, for minus angles, plus angles, I can draw a set of circles. This I call them as N circles. Now if a polar plot is given, I superimpose the polar plot. At a given frequency, what is the closed loop phase angle? I can find out. That is N circle. If I can draw magnitude plot, okay, as well as the phase angle, correct? No, means if I can have M circle as well as N circles on magnitude, so magnitude dB versus phase angle coordinates, I call this as Nichols chart. These are M circles. These are N circles. Okay, M circles or N circles on magnitude in dB versus phase angle coordinates. I have just put them. Now, if I can draw log magnitude versus phase angle plot on this, at a particular frequency, I can simultaneously find closed loop magnitude versus closed loop magnitude and closed loop phase angle. That is what we call it as Nichols chart. Right? This is how we can use all these charts. And that completes our discussion on Bode plots. Here, how to take the open loop transfer function, how to construct Bode plot for each one of the factors, both magnitude plot, phase angle plot, then how to draw the resultant magnitude plot, resultant phase angle plot, then what is gain margin, phase margin, then how to determine gain margin, phase margin, then how to get the system stability. These things are told. After that, from frequency response graph, how to relate frequency response graph with the time response specifications. These things we discussed. How to find steady state error constants Kp, Kv, Ka and all that thing. How to identify the type number, and once the Bode plot is given, how to find the transfer function. Also I told you. In addition, we discussed M circles, N circles, Nichols chart. So now you can think of using Bode plot while designing control systems for frequency response. Thank you.